Alright, so this is kind of an overview of the design history of the counters. So this is currently the new one, but I'm going to go ahead and fly over to the original attempt over here. This one does not work in the slightest, but it had a bit of salvageable technology. At its core, it's got binary counters for each digit. So we have 3 digits on the counter, as will we have 3 digits in all other designs I've showcased here, because that's just kind of the amount of digits I used for my test case. Up here at the top, we have the actual counter. Each one of these pistons represents one of the digits. If this redstone block is either in its retracted state or extended state, dictates whether or not it's a 0 or a 1, retraction being a 0, and extension being a 1. The counter is programmed to reset itself back to 0 whenever it sees the number 10, because that's the first digit that we count up to, where we can no longer write it as a single digit. It requires 2, 1 and 0 in that case. And because of that, we have it reset itself to 0, and we tell the next counter to increment, kind of like the carryover digit whenever you're doing addition back when like elementary school and stuff. Everything after this is kind of just an abject failure. This portion technically works. It's kind of like a pseudo memory cell-ish, but it was kind of a band-aid to a problem that I couldn't fix. And this is really the heart of the problem, is this portion right here. This tries to look at the binary signal and says, okay, which digit is that 0 through 9? And right now it's sitting at 0, 0, 0, the default state, because I have manually put it there, and I'm not going to turn it on anymore because it doesn't work and it'll probably break it again. But these redstone blocks being down were supposed to indicate which digit was the present digit, kind of like how a down block on the counter in binary represented an on state. So that's this. It doesn't really work super well, but you can kind of see the beginnings of some elements, like this kind of spaghetti wiring out front that you're going to see pop up later. As well as that binary counter actually makes a return in the next design, which is located over here. You can see the counter, again, is located in the back of here. However, out front is a completely new system. What this does is it effectively does the job of that circuit that didn't work in the original, that looked at the binary value and said, what digit 0 through 9 is this? And this is, technically it's a decoder, but that's more of a technical term. Effectively, it's just one giant AND gate that checks every single possible combination of binary values ranged 0 through 9 and sees if it's the exact correct bit state with some AND gates. And then after that, there's a display driver. You can see it's different from the original because it doesn't use downward-facing pistons with redstone blocks. It uses a torch tower and this mess of spaghetti wiring. The main advantage to the spaghetti wiring is actually that in the original we used repeaters to go around blocks we didn't want to draw power from, whereas in this case we just literally go around blocks we don't want to draw power from, which adds some bulk, but it does mean that we have very consistent and reliable timings, so that if we were to increment the counter, which I can do with these control lines, all the functioning counters have been given these blue and green control lines for incrementing the counter and resetting it. But we can see that the number appears all at once, and if I give it the command again, we'll see that the 2 appears all at once. Minus a brief issue that is a result of redstone lamp behavior, where they take 2 ticks to turn off, despite taking 0 ticks to turn on. So there's a bit of a delay in the turning off behavior. So the numbers are going to persist a little bit after the value has actually left the counter. If I reset, we can see again that synchronous display behavior where all digits both appear and reappear, or excuse me, they disappear and reappear simultaneously. Moving on to the next design, we have changed the counter for a new design that uses a loop of hoppers as opposed to the binary counter. This is a huge space saver because we're able to ignore that entire yellow decoder section that looks at the binary values and converts them to 0 through 9, and instead we're able to count directly in 0 through 9, which we see on these comparators here. And you can also kind of visually see it more readily with the pistons being extended. Whichever piston is extended and has its redstone block raised is the digit that we are currently reading in the counter, which then does the same act of sending it up through the torch tower driver for the display. You may note that the display on this one is currently completely off as opposed to the 000 state we see in the original functional design. That's because we've added a new feature to this counter, which is something called ripple blanking. What this does is it effectively takes leading zeros and chooses to deactivate the display at that digit instead of displaying a zero. But it only deactivates if it is a leading zero. If it is, say, for example, in the digit 10, that's 1, 0, the zero there is used to indicate place value. We need to keep that and display that zero in 10. So we don't want to get rid of that zero, but we do want to get rid of, for example, again, if we're displaying 10, the counter actually stores 0, 1, 0. We want that zero out front to be gone. So we want to hide that one. So that's what ripple blanking does for us. It's an optional feature that can be removed. It's in this orange section right here. If you don't want it, you can simply remove the orange section and the counter will work exactly like the other one, just faster and smaller. And I've also color-coded the drivers in slightly alternating pink and purple colors just for a bit of visual clarity in this design. The reset line is where you really eat the complexity on this one. Previously, you just had to power the pistons for at least 2 ticks so that they could extend and retract and grab all their blocks into the retracted state, whereas this one needs to use advanced control circuitry to turn off these hoppers, or excuse me, turn off these torches enabling these hoppers, which will allow the items to drain all the way back to the 0 position in their respective cycles, and then fire them back up into the top. However, we need advanced control circuitry because the timing of that is variable depending on which digit we are, because a further away digit takes longer to reach the end. So we can't use hard-coded timings, and instead we have to use detection and memory cells for whenever we are and are not seeing items at the 0 state. So a bit more complicated. This one operates at the exact same speed as the original. Both of them operate at 4 redstone ticks, which is the item transfer rate of a hopper. And that was originally the target transfer rate because I didn't really think it was worth it to make anything faster than that because I was originally intending these to count items. However, I then realized that you could just use 2 simultaneous hopper lines kind of in an arrangement that I tested real quick on the ground down here. But something like this actually is fully functional. You can use this, and then up here you can use a similar thing coming out of the dropper to effectively get double the rate by just using 2 chains of hoppers. And that's what I did. I set out to make a faster clock, and originally this only was able to operate at 3 ticks, but with a small modification I was able to drop it down to 2 ticks. Anything faster than that isn't technically achievable. There are 1-tick clocks, but they are some specialty behavior that kind of relies on unintended subtick behavior. If you don't know what that means, you don't need to know. Most redstone is never going to encounter it. It's definitely not intended behavior, but it is present in the game nonetheless. But for our intents and purposes, a 2-tick clock we can interpret to be the fastest, reasonable, achievable clock for this application. Because anything faster than that would be a pulse every single tick, and there would be no more off state for the counter to be able to tell between the on and off states and the pulses, and it wouldn't have anything to count anymore. It just looked like one continuously on signal. So back to the counter. This one again changes the entire design of the the entire design of the counter again. And this time we use redstone signal strength to store our values. So if I open F3 here off to the right side, about midway down on the screen's vertical height, we see an entry that's labeled power 0 and a corresponding one labeled power 15 on its diagonally opposing redstone dust. The relationship between these is 15 minus the other is going to be its value, so it's always kept in lockstep with one another. And the reason that this is preferable is because we're able to store a whole lot of data in this one piece of redstone dust and then extract it with some circuitry that is out front. This circuitry in the back that you see looping around here is the reset at 10 behavior for the exact reason we had to implement reset at 10 behavior in the original binary counter. And just like the original binary counter, we also see it daisy chaining over to the next digit so that it can increment it when it resets at 10. This one then uses its redstone signal strength. It does a bit of addition to add 1 to the signal so that we can use a red coder even with 0 signal strength present in the counter. If you're unfamiliar with the red coder, there are some resources on YouTube on these. They're a pretty old design. Just keep in mind that there was an update where they changed the behavior of redstone dust. I think it was 1.16, but I'm not entirely sure. where designs older than that sometimes will not work because of the way that redstone dust routing was changed, and what isn't is not powered by diagonally moving like up a diagonal redstone dust. So keep that in mind if you look for designs online. But this red coder pretty much just says, all right, whatever digit was in the counter that we've added 1 to, so in this case, if it's got a 0, we're actually feeding signal strength 1 into the red coder, turn on that signal strength torch. So because we fed in 1, we get the first torch. If we were to feed in, say, 4, we would get the fourth torch. It's worth keeping in mind, again, because we've added 1, 4 redstone signal strength to the red coder actually corresponds to 3 in the counter itself. And this is perfectly reasonable because the first digit we display is a 0. So that's kind of where it is, where it's a 0, but it's the first digit, so we need to feed it 1 signal strength. And then above this is pretty much the exact same display driver from before, except it's been slightly modified out front with this red region. This gets a little bit of space saving, and then it's 1 block slimmer. So that is a nice little benefit. It's also 2 ticks faster on this red region's wiring. So to kind of give an example of just how quick these things run, I am going to put some test items into here. This one uses a chest for its timer behavior. So we can see this one's running. Fairly respectable speed. And now if I go over, this one does not have an item counting clock hooked up to it. I just hooked up the clock directly in this case. But if I were to turn its clock on, we can see that this one is moving at a significantly accelerated rate of counting. So even now, the faster one has already passed the original, and this one is probably going to, it probably would lap it if it could. I'm not going to let it go that far because we all have places to be and things to do. But if I go over and, actually real quick, let me turn this one off and then let me pull the test items out of this counter. Oh, that's putting more items in. That's very not correct. So if we look at both of these, this one got to 96, whereas this one got to 162, and I gave this one the benefit of the doubt of first being started before the other one and me taking its items out after the other one. There's some additional oddities in the reset behavior, so if I reset this one like this, you will see that there is some brief flashing of the digit 0, and what digit it appears at is kind of inconsistent between the 1's place and the 10's place, but that's a result of the fact that resetting a higher value digit takes more time than a lower value digit, and that in combination with the ripple blanking just adds some oddity to the behavior. However, with resetting this one, because if you recall, those redstone dust diagonally opposing pieces were kept in direct lockstep with one another, it's always 15 minus its opposing pair, we can simply fully power the opposite piece of redstone dust, and that will force the other piece back to 0 signal strength, effectively resetting the counter. And that's what this wire actually runs to. So if I do this real quick, you can see it just immediately resets all the counters. And you can actually see that behavior of using a torch to fully power the opposing redstone dust right here. Additionally, we use another redstone torch wired into the counter itself for that reset at 10 behavior. So that torch powering the diagonally opposing piece for reset is used in a couple places here. So yeah, that's pretty much the counter. If you want the brief functional overview, you've got the clock input that is right here, fed into 3 counters, daisy-chained in modules. Each counter is effectively a redstone signal strength memory cell / adder that resets itself whenever it reaches 10 and then chains it over to the next counter. After that, we add 1 to the signal strength to comply with how the red coder works for decoding the signal. And then the digit that we want, 0 being at the back here and 9 being closest to the display, will have its torch turned on, corresponding with whichever redstone signal strength is present in the counter. And that is going to make its way up the display driver and then to the display. So that's the design. And you can kind of see how it evolved over time with not working at all to working but huge to working but smaller to working smaller and faster. In fact, I don't think I can make it faster. So, yeah, There it is.